We just had an office hour session, so we're going to share this much in here about quickly sketching the graph of a function that is given in factored form. So the functions are given in factored form. Reading off the multiplicity is really easy, so we're not going to do that in here. And computing the end behavior a little bit more involved than when it is given in the general form, but it's not that bad. So you calculate the end behavior and record the multiplicities. So if it is an end behavior going up or up here, or down, down, or opposite direction, there are 4 possibilities for end behavior. So you wrote them down, and the multiplicities is all attached to each of the zeros, so you plot it in the x-axis. For example, let's say that that one has odd multiplicity in there, x to the third, or x to the first, or things like that. I forgot to include the x to the first cases here. It's supposed to be a straight line. So let's say there was odd multiplicity 3 or higher. Then you're going to put this one in there. But you have to think about the choices. They're going to be a flipped up version in here, or this one as you see in there. It is determined the first one all the way to the right. Don't start in the middle here. You have to start in the right. And it is determined by end behavior. Once you determine the direction of this one by the end behavior, rest of the part is completely determined by how they fit together. So don't look at it in here and not doing anything else, and think about which one is it going to be. I know it's even, but is that going to be concave up like this, or is it going to be concave down? Don't ask that question to yourself. Just start from the right, use the end behavior, rest the part. As you go to the one at a time, it is completely determined. For example, because of the end behavior up here, if it is at degree 3 or higher and odd, it must be in that shape, so that in this direction it fits together with the end behavior. Suppose next one is even, so I know I have to use this one, but it's a choice that is that going to be concave up or concave down. Because things are moving continuously in a polynomial functions, because these guys were in the lower half of the plane, this should come from the lower half of the plane. So I just copied one version, that is flipped down version, so that if you patch it together this one like this, so that when you come from here to there, you stay in the lower half and does not cross it again. If you cross it again, you know you have to introduce another 0 there, but this is a complete list of 0. So that kind of explains nicely why that has to be in the low below. And then you have to connect this one nicely like that. All right, I kind of try to do that. Let's say that one's degree 1. Okay, the multiplicity one, I'm sorry, let's say that one is a multiplicity one, so you have to use this one. So you have this version or the other version in here. But because when you go from the right to left, we're still in the lower half of the plane, so you have to come from the lower to the upper. So that seems like a flipped up version of this one is a right choice. So I copied it here. So if it is lower half plane, and that naturally connects from lower half plane, and using the straight line, it must go up like this. So that's how I choose that one, if the multiplicity there was 1. So you're going to read off the last multiplicity here, and that must be even case. If it is odd and you go down here, it doesn't match the end behavior, put it up there. So that is already determined at the beginning of this problem, and you're patching together from right, one at a time to the left, and at the end it must coincide with this remaining end behavior. If this doesn't coincide, you must have done something wrong. So I'm going to say this is even multiplicity in there. So this guy's even multiplicity guy, so we have to think about whether it's going to be concave up or concave down there. But preceding one was over in the upper half plane, so this guy must remain the upper half plane as you enter the zeros in there. So if you think about both choices there, this one is the one that when you go from here to there, it doesn't cross x-axis, so it doesn't introduce any more zeros in there. If it is flipped down like this, you can see you gotta cross it like this. So you have to introduce another 0, which is not allowed. So again, that's a nice explanation of actually how they patch together and how to determine the up or down property coming from the right. So I hope you agree that if you start from here, given by this end behavior, kind of determines up and down all the way to the left. so this is the, and let me just finish up this bit and bits in here. All right, kind of roughly sketch this. So this is the final picture. Given, started with the end behavior and all the multiplicities written on here, and then you end up at this type of picture. But if you look at it here, and don't think about the procedure we went through, just look at it here, I want to know how to determine whether it's down and up. Of course, there is an answer with X squiggly symbol C that we did in class that tells you how to go directly to one of the zeros and determine the behavior right away. There's a way to do it, but if the goal is just sketching the graph of this function, I think it's more efficient to do it this way and then patching it together, go from right to left.